the largest of those numbers. So the biggest number of choices in a rule. In one of those many rules, it will have the largest number of choices on the right hand side of the rule. Call that largest number little b. Okay. So an address. So you might have let's say a root node here, and then maximum you will have little b children. Okay, the next generation. And then maximum, those child nodes in turn can have maximum little b children. So the parent node now has maximum b squared grandchildren. Okay. Now, so if you go down, several layers, you can now give an address by specifying, like at the root node. Say, well, here, I'll give you an actual example. Here's an address here. And an address is of what? You're addressing a node. You're specifying the location, if you like. That's why it's called an address. You're specifying the location of a node in a tree. Whose tree? Well, n's tree. N's computation tree. And at each node corresponds to a configuration of the machine at that node. Okay, so here's an example of an address of a node. So 2, 3, 1. What does that mean? Okay, well let's say 4 is little b is 4. So maximum the rules they'll have 4 children. Maximum 4 child nodes from each parent node. Maximum. Okay, right. So 2. Now look at it from your perspective. So here's the root node, and then you go 2. So it's 1, 2, 3, 4. So 2 would take you to this node here, this child node here. Okay, and then the next one is 3. Now, from respect to relative to this node here, let's say it could have maximum 4 children, and then the next one, the next digit in the address is 3. So 1, 2, 3. So now you're here at this node. Follow that? So you took the second node with the first step, and then you took the third node, your child node, with the second step, and then the third step you'll take the first node. So I could draw it. So just imagine. Right? So you took... Oh, damn. Sorry. 2. Okay, so 2, 3, 4. So you took the second option. So here's your root node here, let's say. And then 2, so they'll take you to that node there. And then 3, well, that'll take you to that node there. And 1 will take you to this node. Okay. Now you at each position, like at each depth, if you like, in the tree, you specify 1 digit, and these digits they range from 1 to little b. Fair enough. So that's how you find the address of each node. Now you may argue, but what about? I mean, you're assuming that like b children each time. That's not realistic. There may be only, well, in most cases 1 child, sometimes 2 or 3, but not every time 4. Agreed, sure. So often you can, like if you went, so we just had 3 layers. What's the maximum number of leaves you could have in this tree? Well, it'd be 4 by 4 by 4, right? 64 leaves would be the widest possible tree you could have. 64, in other words, 4 cubed, 4 by 4 by 4. Yeah. Okay. Now, most trees won't be like that. So you could. So if you had, you could have all addresses ranging from 111 up to 444. Okay. Now there may be some addresses that, take this as an example. Say the root node. Well, so we had a tree something like this. So the parent node, the root node had just 2 choices, and then this node had 3, and this one had 3. And say you have an address is imagine 344. So you had that address 344. 3. Well, there is no third child. Okay, so that address is invalid. Okay, and you can have lots of invalid addresses. An invalid address meaning it doesn't correspond to the reality of the tree. Right? The number of branches, number of choices from one node to the next layer may be more limited than 4, maybe less than 4. Okay, so you can have addresses that are invalid. They don't. There is no such node. For example, this tree like this, there is no such thing as a node having address 444. It doesn't exist. Right? It's invalid. So you'd have lots of addresses like that. Now, why am I saying that? What's the point of talking about invalid addresses? Well, you'll see that will come out in the algorithm. It's not clear at the moment. You know, as I was writing it out, I was puzzling. You know, what's the point of all this? But it'll become clear, and that's the beauty of a prof. The prof breaks the ice, sort of explains things, hopefully, so that you'll save the effort of having to do that yourself. And I'm not sure if that's a good thing actually, because you know, when I get puzzled, that's when I learn. And you know, I do get puzzled. I'm reading through. Why? But you know, how do you specify the address? Where does this address come from? And what does he talk about invalid address? What does that mean? It wasn't until later, until I got into the details of the algorithm. That's where it came from. That's why. But you know, as we're going through, you don't know that unless you're told. So, okay. All right. Now, before I get onto the nitty, even lower level details, this address, what's going on? Now, remember, this is the contents of the tape at a particular node going down a particular path or a particular branch in the tree. Okay, so this is getting updated. It's the contents of the tape, ends tape, at a particular node in the tree, and as it goes down the branch, the contents of the tape will change because it's getting written on, overwritten, and so forth. And this is the address. Okay? So as you go down, you may ask, where does this address come from? Next session. Okay, but given that you have this address in the third tape, what you do is you just go down from this node to that node, right? So each step here, you're going down a further node, deeper down the tree, and at each node, of course, there is a configuration. See, you're given the tree. You're given that. You're trying to simulate the tree with using D. Okay, so the tree is given. So you use this address. So you go down the first branch to the child node, and then the child node you go down the child's second branch from the child node, and then you get to a node, and then you go down the third branch of that node, and the third branch of that node, and so on. And at each node, you pick up the configuration, and you plug that information from the configuration, like the next state and so forth, and you plug that into the transition function, and you calculate what you can update this. You can update your current string, your current tape at that at each node. Okay, so what's left to explain under that next session is where does this address come from, and how do you go about for different paths you're going to need different addresses, a different sequence of node. The second branch of that node, and then you go down the third branch of the child node of this one, and so on. So how does this get changed? That'll be for next session.